Good morning, everybody. Thank you for joining us for our webinar, Utilize Abaqus to Solve Contact Problems and Troubleshoot Convergence Issues. Our webinar will be 1 hour long. We'll have a 15-minute Q&A session at the end, so if you come across any questions during our presentation, please ask us, and we will be happy to respond at the end of the presentation. I would like to get started with a brief introduction to our presenter. He's Syed M.M. Jaffrey, who is our Senior Simulia Application Engineer and FEA Specialist at VIAS. Syed has a PhD and a Master's in Mechanical Engineering. He has over 10 years of experience with Abaqus, working extensively with local and global FEA of subsea structures and components. Now we'll get started with a brief introduction to VIAS. Syed, would you like to take over?
Hello, good morning, everyone. Thank you, Beatrice, for your kind introduction. And everyone, this is Syed M. Jaffrey from VIAS, Houston. I'm going to be giving this webinar on the important topic of utilizing Abaqus to solve contact problems and troubleshoot convergence issues today. This is a fairly broad topic, and all we will be able to do is to just briefly go over some modeling tools, modeling tips and tools. Definitely, I mean, this topic is a very broad topic, and it requires several days of training, if not several hours. So we will only be able to touch over a few salient aspects of some important aspects of these problems. So this is my agenda here today. So VIAS overview. So I will be talking about who VIAS is and what do we do. Then coming to our main technical topic of nonlinear modeling in Abaqus, defining contact in Abaqus, convergence problems and their solutions in Abaqus, followed by the question and answer session. So company overview. So who we are. So we have experts from multiple industry experience. What we really do is to provide engineering consultancy, software support, software resale trainings in the area of simulia and simulation, and mainly for resource systems. So we work with several industries across the globe, and these industries are oil and gas, machinery and equipment, petrochemical, process, nuclear, aerospace, medical devices, manufacturing, and automotive. So we have our main headquarters in the USA, and we also have the offices in Canada and India. So our team basically consists of mostly subject matter experts and highly accomplished individuals who have master's and PhD degrees in the areas of solid mechanics, fluid mechanics, materials and corrosion, numerical analysis, FEA, optimization and reliability, data analytics. So as I mentioned to you that we are the platinum value-added reseller partner of Dassault Systems Simulia Abaqus. So our main work involves with Abaqus, but not only this, we also provide the consultancy and training in the iSight, FESafe, Tosca, CATIA, which is the CAD software, Delvia and Enovia. And as I mentioned to you that we provide extensive engineering and consultancy, PLM consultancy, training for the software sales and supports, automation and customization. So we basically would be developing some sort of scripts, Python scripts, and customization type of models for some customers who have some specific needs in some very specific area. And we provide several trainings of Abaqus throughout the year, Abaqus and other supported software throughout the year. So if you are interested in any training, you can register online at our website, and then we can provide either the training in our Houston office, or we can go to your site to provide the training. And we can also provide the online training. So our technical capabilities, as I mentioned to you, that they extend to several areas and we cater to several industries. So we do the conventional component design and validation using simulation, hardcore simulation such as Abaqus finite element method. And then we do the FEA-based fracture and damage mechanics, engineering criticality assessment, so fracture modeling, and the damage evaluation. So these are highly complex and nonlinear models that we do here. Design optimization and reliability using the iSight and some other tools. a structural analysis, vibration assessment, also in the area of the dynamics, electromagnetic systems, using the CST software, such as for the simulation of antenna and some other devices, multi-physics simulations. So those softwares, I mean, using these tools and with the capabilities that we have, we can perform highly nonlinear simulations involving multi-physics type of phenomena, SN and EN based fatigue analysis as a function of temperature, composite analysis and modeling, simulation automation using Python scripts and any other tools, and digital mockup development, system engineering. So CFD capabilities, so we have large spectrum of CFD capabilities comprising of the combustion, separation, fluid structure interaction, acoustic source modeling, and so on and so forth. So as you can see from here that we can cater to multiple industries, and we have high simulation capabilities. And we also have some partners through which we can perform the material testing in simulations. Like, I mean, we perform the simulations, but we can also do some field testing in collaboration with some other partners. We can do the research and development. We also impart the courses at curriculum at University of Houston, training and short courses, some customized trainings. We have our presence felt in the symposia and the consultations. So we have the personnel, we have the staff who are not just performing the testing and microscopy or just performing some overview. I mean, we have the experts who can perform the in-depth study and who have the in-depth understanding of the system and implication of the interactions. So value proposition. So as you can see here, we are committed to every client success through technical excellence and innovation. And so we provide the simulation services, we provide consultancy, we give them the suggestions, we prepare the models from the scratch, and then we perform hardcore, very highly complex nonlinear simulations. So this is because of our domain knowledge in FE and expertise in multiple industry applications. We can also review the existing simulation workflow process and give some good suggestions or improve them. We provide, and we can also provide the computational services. We provide the customized and standard introductory and advanced trainings for the introduction to Abaqus to highly complex subjects in Abaqus. So we can, as I mentioned to you, in-house, on-site, and online. And we also offer the software development services for Abaqus, which include user subroutines, so customized user subroutines, which can be utilized for the material modeling, some boundary conditions, the loading phenomena, or some other complex area that cannot be directly modeled using Abaqus CAE or input file, user elements, Python scripts. So we allow the which allows for the pre and post processing features and calculations on a very advanced level. So these are some of our customers here in consultancy for the FEA. These are some of our customers. So you can see some notable names such as Shell, BP, Kinder Morgan for the pipelines, etc. Then for the CFD, we have BSEE, ExxonMobil, Technip, Genesis, Halliburton, so NASA, etc. So these are some of our notable customers. We provide the software, services. We sell the software to several customers, and then we provide the after-sales services, which include the training and the consultancy to these companies such as IMAS, Geodia, AFC, SWRI, and we are Boeing is one of our regular customers, besides several other customers for the training, as far as the training is concerned. So this basically concludes our introduction, who we are. Now I will get to our technical topic here. I will begin with the nonlinear modeling in Abaqus. So most of you, I mean, I'm assuming that most of you might be the advanced users. Some of you might be the new users to Abaqus, but we all know from our background that most of the modeling which is required in the real life, in real industry, is basically inherently nonlinear in nature. A simplified linear approach has its own limitations and may not always give you the accurate answers. And whenever you are talking about involving the contact or the material nonlinearity, then you simply have to revert to the nonlinear modeling. So from a strict structural mechanics point of view, there are three main sources of nonlinearity which are present in a structural mechanics problem, which involves contact. So either a hard contact without friction or with friction. Large deformations, such as whenever a structure is undergoing large deformation under the influence of the forces or moments, or it undergoes rigid body motion. And the material nonlinearity, which basically means the nonlinear stress-strain relations. So what happens due to these sources of nonlinearity is that the governing equations of static equilibrium or the governing equations of motion, they become basically nonlinear in nature. They may involve then the nonlinear terms. They may then involve some coupling terms between different coordinates, which makes the solution difficult. And then the problem is said to be nonlinear. So when we talk about the contact problems, they arise in several applications, such as flange seals, such as in oil and gas, automotive car brakes, tire road interaction, gear meshing, car crash simulations. Large deformations, they arise due to the rigid body motion of the structures, which leads to coupling of forces and moments, as I talked already. Material nonlinearity arises because of for example, if you are dealing with the rubber simulation, or if you are dealing with the seal simulation, then you have the hyperelastic material, very complex material, and the equation representation is very difficult, and it involves the nonlinear stress-strain relationship. Metals, so even the metals such as the steel, which is very commonly used in oil and gas industry, that may have complex behavior, stress-strain relationship, such as the work hardening relationship. And for the geomechanics foundation, when we are talking about soil, it's even more complex. And there are several models which are present in Abaqus, which allow you to model the soil. So to say that nonlinearity is present in everywhere pretty much, and it is basically our judgment call whether we want to model something as linear or nonlinear. But whenever you will be going into the real world problems, then you will be facing the nonlinearity. So with nonlinear problems, there's a penalty that you have to face the problem of convergence. So there might be convergence, there might be some very simple nonlinear problems which may not give you any hint that there is any difficulty, but then there might be some very difficult nonlinear problems which may give rise to the convergence issues. So here, strictly in this webinar, what we are talking about, what we mean by convergence is the solution procedure convergence. So you can talk about like mesh convergence, or the experienced FE users know that there's something called the mesh convergence or the time convergence, time integration accuracy convergence. Here we are strictly talking about the nonlinear Newton-Raphson method convergence in this webinar. So this is the basic solution itself. So we will review the methods and techniques in Abaqus to define the contact and troubleshooting the convergence problem. So we will not be talking just about the contact, but also the other two sources of nonlinearity, which involve the large deformation and as well as the material nonlinearity. So here, as you can see from this simple stress strain curve, that there's a metal which is undergoing a plasticity, and this plasticity can be dependent upon the temperature, which makes the problem even more complex. So repeating again, geometric, material, and the contact are the three major sources of nonlinearity. Here you are seeing a problem in which there's like a Jones bumper of a car, and it has all three sources of nonlinearity present. So I mean, in real world, in general, you may have all three sources of nonlinearity present. So the good thing is this, that Abaqus offers sound capabilities to tackle these complex problems through standard solver and explicit solver. So, for example, when we are talking about how to model a nonlinear large deformation problem, so this is defined at the step level. So if someone is wondering that how do I turn on the nonlinear geometry option, this is where you turn it on. So when you are at the stage of creating a step, so there's on the default, you always have an option of nonlinear geometry off. So if you know that your problem is going to be complex, and it may generally involve the nonlinear geometry and large deformation, then you should turn this option on. And most of these tools, all of these tools to render the nonlinearities in Abaqus are accessible to the Abaqus CAE graphical user interface, which is easier to use for at least for the beginning to intermediate users. Similarly, you can define the complex loadings and materials either through the keywords or user subroutines, or directly through the Abaqus CAE interface. So here, if you go to the property module, Here I'm on the left side, on the left panel, you can see that I'm defining steel material. So you go to the mechanical and then you say select plastic, and then you can start defining your yield stress as a function of the plastic strain. So this will complete like, I mean, in this way you can generate your stress strain curve. So in the elastic regime, you will need to specify the modulus of elasticity and Poisson's ratio, but here in the plastic regime, then you can define your complex material behavior, nonlinear behavior for the material stress strain for a material. If you are trying to define a rubber hyperelastic material, then you do have the tools to define those types of rubbers. So you basically select, go to mechanical and hyperelastic materials, and then you can proceed on defining whatever strain energy potential of whatever model you are selecting, and then you can proceed on to define those coefficients which will model the rubber behavior appropriately. Or you can directly import the test data inside Abaqus, and then you can do a curve fitting between the imported test data and the theory which is present, and then you can take the best fit curve out of those selected theories. So you also have tools to do the calibration of a given material model, or to do a curve fitting of a given material hyperelastic model inside Abaqus CA interface. As far as defining the contact and interaction properties, so you go to the interaction property module, and you can define the interaction properties directly from there. So here, this is as you are seeing on the left side panel. So tangential behavior, you can define your coefficient of friction, your traditional coefficient of friction, which is the Coulomb's friction, or you can select any more complex material, interaction property model and define the parameters accordingly. The normal behavior, you can select either as a hard contact. So I will be discussing it a little bit in more detail when we proceed further. So, and then on the right-hand side, then you can define, for example, a general contact and assign the global interaction property that you have selected, and you can individualize those property assignments also to different contact pairs if you have multiple bodies coming into contact in your model, and then you need to define the interaction properties separately. So basically the solution procedure, so this is like a hypothetical curve that I'm showing you here on the screen. What Abaqus is trying to do in the nonlinear problem and in solution of a problem is this. Suppose that you are plotting this load versus displacement curve. So this green curve is the one which is your actual numerical equation. I mean, that is what should be followed. I mean, this is what the actual true curve would look like if you were to solve your problem successfully. So this is the true relation between the load and the displacement. So what Abaqus tries to do is this, that it starts with an initial guess of the displacement, and then it calculates the and basically whatever load you have applied, the total load that you have applied in that increment. So it calculates a tangent stiffness matrix. Based upon the tangent stiffness matrix, it comes up with a correction C1 that you are seeing here, and it recomputes this displacement. Then it recomputes the tangent displacement, tangent stiffness matrix, and it keeps going on. So basically, this is the graphical description of the depiction of the Newton-Raphson method. So it keeps going on until it intersects this P total line, and then from there, it drops down to the actual numerical equation. So where is the numerical equation? That is in your model. That is in your model. So I mean, Abaqus doesn't know, of course, a priori what is the equation, what is the actual solution. This is where it is trying to converge to. So once you basically it keeps doing it, and it comes to the problem where the total load is, and where the residual, which is the I1, is within certain limitation, which is like 0.5% of the applied load. Then Abaqus stops over there, and then you say that your increment has converged. But for some reason, if it started with an incorrect increment, or for example, if the problem was not well posed, and we will be talking about what is a well posed and not well posed problem, then this procedure may not converge, and then you say that the solution is not said to be converged, or said to be having the convergence problems. So I mean, examples of nonlinear problems, if you pick up from several industries. So here you can see that you have the contact, you are deploying the pipe, from the reel onto the seabed. So you have large deformation of the pipe coming into the seawater. Then you have large nonlinear forces which are acting on the pipe from the waves interactions. then you have the contact interaction, you have material nonlinearity, you have all three sources of nonlinearity present. If you take a look at this platform, then you have this contact between the braces and the stiffening structures, and then you have material nonlinearities. Here in the car crash simulation, then you have all three sources of nonlinearity. It's a dynamic simulation, highly complex problem. So Abaqus is typically very capable of solving and handling these types of problems. So it has got very robust algorithms. But just a word of caution that having a robust algorithm does not mean that, I mean, you can give whatever type of problem to Abaqus. I mean, you still have to make sure that all of your inputs and all of your problem is well defined, parameters are right, because I mean, Abaqus simulation will give you what the user has put in there. Here you are seeing a foundation pile buckling, like a general foundation pile buckling. It is undergoing the large deformation, and then the material nonlinearity is also taking place, and possibly at some points it can also undergo the self contact. So these are the sorts of problems that you can solve using Abaqus. So once again, we as analysts have to be careful that, I mean, even though Abaqus has got very powerful algorithms, but we should be careful about putting the correct inputs in. That's how we'll be getting the correct inputs or outputs. So breaks skill analysis, here it involves contact and friction. So it's once again a complex problem to solve. And then it's a shaft seal, very prevalent type of problem in the oil and gas industry. So this is a rubber shaft seal, and then it has the hyperelastic material. Then there's contact also involved. So once it is installed into place, it's a completely nonlinear problem. Pipe flange analysis, so contact between the bolt and the flange face. So I think I will be having an occasion to show you a similar model later. And then you have this this seal between the flange parts, and then you have the bolts here. So completely nonlinear type of problem. Foundation pile. So as you can see, this gray body is a foundation, is a pile which is being inserted into the soil, and then the soil undergoes the deformation. Soil itself has a complex nonlinear behavior. So soil undergoes the large deformation. It has material nonlinearity, and then the pile also pile is inducing this large deformation in it. So these are the domains of Abaqus and beyond, where Abaqus can be used for the solution of nonlinear problems. Similarly, you can see this pipe lay analysis, so which is the pipeline analysis, very important problem for the subsea industry as well as for the onshore industry. So the pipeline can undergo the buckling nonlinear, the buckling and large deformations and thermal expansion. And contact, it has got the contact with the rough seabed. So in general, it's a fairly complex problem to solve. So now, how do we define? I mean, we saw that there are so much contact problems in Abaqus and bodies coming into contact with each other. So how do we define the contact in Abaqus? So Abaqus has got some powerful tools. So before we go into those ones, let's talk about three main ingredients which are necessary for defining a contact in Abaqus. So the contact discretization. First of all, between the two surfaces, as you can see, there's a red surface and another surface which is hatched here. So we are trying to define the contact between them. So we should see the discretization. By discretization, we mean whether we are going to be defining a node to surface or surface to surface. I will be discussing a little bit more about this. Constraint enforcement. So what type of, how do we mathematically want to formulate it between the, as a normal contact? So there will be a normal force which will be developed between the two bodies, and then there will be a tangential force if there's friction between the two bodies. So the mathematically, how Abaqus is going to take care of it. So Abaqus provides three main algorithms in it, which is direct algorithm, which is the Lagrange multipliers, also called as Lagrange multipliers, penalty method, and then third one is the augmented Lagrange. And contact tracking, so finite sliding or small sliding. So let's talk about all of those aspects. So node to surface, it considers the contact between nodes on slave surfaces to facets on the master surface. So it basically, when you are talking about the node to surface, you are saying that, okay, the node on this green line, the blue dots on the green line, for example, they will be coming into contact with the faces. So okay, I mean, this was an initial developed algorithm when Abaqus was in its initial time, like in late 60s or maybe in the early 70s. That is when Abaqus was defining those types of those types of contact algorithms. So at that time, node to surface was the historically developed the first algorithm. So I mean, although it was like I mean successful to some extent, but it has got some limitations in it. What it says is that okay, I mean the node can come into contact with the surface faces. But for example, what if we have like not very fine nodes and not very fine type of surface facet on the other hand, and then a node can penetrate inside the surface, which is not physical. Computationally, that is efficient. So, but the problem is that penetration between the surfaces may occur. It does reduce the solution cost, but it has got limited accuracy. Now, the next, with the advent of high-speed computers and the world we are living in right now, with the high-power computers that we have, now there's a better algorithm which considers the contact between surface facets directly. So, I mean, if you do not have nodes strictly and then you have surface, then it is better to actually utilize the surface to surface contact formulation. So then what you will be talking about is basically one surface coming into contact with the other surface rather than a node to node. So then you have surface facets coming into contact, and then possibility of penetration is decreasing here. So it has wide applicability. Now you have high-speed computers, you have large number of processors, so you can submit your jobs at the higher speeds, and then you don't have to worry about the solution accuracy. Well, you have to worry about the solution accuracy in that sense that what formulation you described or what constraint enforcement you described it, but otherwise this is the more reliable method as compared to node to surface. So recommended to use because of large computational power. So as I was discussing about this constraint enforcement, so constraint enforcement, so generally you can achieve the hard physical contact using these direct Lagrange multipliers, penalty method, or augmented Lagrange. So as you are seeing from this picture here, so when the body, for example, this ball trying to bounce onto this wall, then there's no penetration, so no constraint is required. So that is before the contact is established. When the body comes into contact with it, then the constraint is enforced. So positive contact pressure on the body is developed from the wall as an action and reaction. Okay, so if you wanted to plot it on the graph, so the red regime on the horizontal axis means when there was no contact. So this is on the horizontal axis, I have the penetration or the displacement. Then on the vertical axis, I have the contact pressure. So then once the bodies come into contact with each other, any pressure is possible in during the contact. So that is the definition of the hard contact. That is generally, ideally, that is what you would like to do. In physical problems, that is what would happen. So direct enforcement, this allows you the strict enforcement using Lagrange multipliers. We will not be going into the mathematical details of what the Lagrange multipliers are, but simply speaking, there are certain factors which are added to the equations, dynamic equations or the static equations, so as to bring about the normal force and to make the equations of equilibrium in such a way that the normal force is developed whenever the contact is developed. So there are certain alternatives. So some problems you can solve easily using the direct enforcement, but then there are other classes of problems, for example, which involve hyperelastic materials or which involve soft type of materials in which you try to do the direct enforcement and the solution may not converge. So then once again, we have to look at the problems in this webinar. We are talking about the contact as well as in the context of the convergence, strictly because we want solutions to come to a reasonable, reliable end. So then what you do, that Abaqus provides you the option of using the penalty enforcement. So what penalty enforcement does is that instead of taking this vertical green line, which means infinite slope, which means the contact pressures is like, I mean, it can be anything, and hence the dP by dH is like infinity. It tells you that, okay, I mean, you can do a little bit of penetration, so it's some numerical softening. So you can allow some numerical softening. What it means is that the surfaces can penetrate a little bit. I mean, this little bit really has to be just in the context of your problem. Of course, you cannot allow like a penetration to be like 1 meter between the bodies, or like maybe 10 centimeters even, maybe like 0.1 inch, 0.01 inch, or like maybe speaking in millimeter, maybe a couple of millimeters. But if your scale of the problem is very small, if you are dealing with like a micro-mechanical type of system, then all of these tolerances may have to be decreased accordingly. So I mean, it depends upon the scale of problem that you are talking about. So then the penalty enforcement, it says that, okay, this blue line may have a little bit of slope. It doesn't have to have the infinite slope, so that some penetration may occur between the surfaces. Maybe the solution will not be 100% accurate. Maybe it might be, but still it may help in converging solution, and it may help in maybe you may get like about 90-95% reliable solution. So this is like some sort of compromise from your exact direct physical situation because of the convergence issue. Augmented Lagrange method, so approximate enforcement is done using the penalty method. So it is, you can kind of think that it is something in between the direct enforcement and the penalty enforcement. So it does allow you some feature of the direct enforcement, but it allows you a little bit of penetration between the surfaces. So basically, the last two methods, penalty enforcement and augmented Lagrange, are approximate methods, you can say. So here, I mean, if we try to look at certain comparisons of the problem as to what happened. So I'm just, without going into any details, I'm just showing you that this on the left side here you are seeing an example of a classical Hurst contact problem. So if you use the direct Lagrange, then you can see that which is the most accurate method. I mean, no penetration. Then you are seeing that stress is 1.21 e to the power 5. If you go with the penalty default method, then you are seeing 1.183 10 to the power 5, which is only 1.5% difference. Then the augmented Lagrange, if you are looking at it, then you are looking at 6.34, which is a considerable difference. So I mean, some of the time, all the numerical methods may not work exactly in the same way for all types of problems. Now, on the right-hand side, you are seeing 3-point bending specimen. So when you talk about this one, then the direct Lagrange requires 130 iterations, and the stresses are pretty much almost identical. And then the penalty method with some stiffness of the surface, this basically leads you to 112 iterations, which is a less expensive solution. So this may basically give you the results faster and with almost no difference in the stresses. So these are the judgment calls which basically come from the experience and usage of the software, and then you have to perform some sort of I would say sensitivity studies. So in the summary, so comparison of direct versus penalty method. So on the left side you are seeing direct enforcement Lagrange multiplier method, which is the most accurate one. But physically, I mean, sometimes you may have the convergence issues because of the hard contact. So it's exact constraint. So it will give you the exact result. Disadvantages: Lagrange multipliers, they add to the equation solver cost. So in general, it might be more computationally expensive, sensitive to shattering. So it may lead to the convergence problems. Shattering means the surfaces are like sliding from each other, and the contact is and then there might be multiple constraints on the surfaces. So this may lead to those problems. Difficult to treat the over constraints in this method. In the penalty method, on the other hand, you have improved convergence due to numerical softening. But then you are and then also you do not have Lagrange multiplier degrees of freedom, and it avoids the over constraint issues. But the disadvantages are a little bit of small penetration exists. So need to adjust penalty stiffness in some cases for this method to work. Contact tracking means, so the third and last ingredient of defining a contact problem means, so in this one, contact tracking is finite sliding. So generally, I mean, if you have enough computational power, you should go with the finite sliding. Its general applicability, so point of interaction, the master surface is updated using two representation of the master surface. So what the small sliding does is this, that it assumes that the master surface is always moving in a straight line, and it follows that one. But it has, like, I mean, when you are talking about large deformations or large sliding, then it has limited applicability. So it's approximation which is intended to reduce the solution cost. But I mean, if you have powerful enough computers, then you may want to just use the finite sliding. If you are anticipating the large sliding, and I mean, if there's like a rough interaction between the two bodies and they are not going to be potentially sliding, especially in a static problem, then you should be going with the small sliding problem. Small sliding contact tracking formulation. So here I'm just showing you some interesting tools from Abaqus. So here, as you can see, on the module panel, on the toolbox panel, you are seeing this green flashlight symbol. So what this allows you to do, and here in the model, you are seeing the flange model, which has got many components, like multiple components. It has got the flanges, and then it has got the hubs, it has got the boards, and nuts, and then it has got the seal here. So multiple interacting surfaces here. So if you, there are two major formulations through which you can define the contact between the bodies. So the contact pairs. So this flashlight tool, this basically allows you to automatically detect the contact pairs. So what Abaqus does is that once you have assembled all the points or all the bodies in your assembly properly, based upon their distance, and you can specify within which tolerance, then you can activate this tool. You can automatically find out the contact pairs, and then you can define them through this find contact pairs tool. So the advantage of using this approach is this, that you do not have to individually go and define the contact pairs. So this is a fairly fast tool, and it really helps when you are talking about the contact pairs. Then there's an even more powerful tool here in terms of the general contact, in which you don't actually even have to go through this procedure. You can just activate this general contact tool. By the way, both of these are available from the interaction module. So you just activate this general contact interaction, and you just define the global interaction property. Then you can individualize the property assignments, and then you are done with the contact definition. So it is that fast. However, the disadvantage is this, that in the general contact, Abaqus tends to see that every body may contact in every other body in the assembly. So this may make the computational cost a little bit higher. In setting up the model, it is one of the easiest way, but in solving the problem, maybe it may take a little bit of more computational time. So general recommendation is this, that if you have a lesser number of bodies, and then you are seeing that some of the bodies, they cannot really come into contact with the other one, then you may want to just go with the contact pairs rather than the general contact definition. But if you have high number of bodies, and right from the beginning of simulation, you are not sure which body may come into contact with the other one, then it's better to define the general contact. So now we will be talking about our last phase of this webinar, convergence problems in Abaqus and how to solve them. And once again, we are just talking about the overview of them. Overview of the problems. We are not going into much of the details. It's a very broad topic, as I mentioned to you. And then we offer the courses also, which talk about these types of problems, and we provide extensive workshops. So if you are interested, then you can register for these classes. So coming back to our topic, convergence problems in Abaqus. So the most common convergence issues in Abaqus are numerical singularities. So you'll be seeing several types of error messages or the warning messages in your STA file, your status file, and through the job diagnostics tools or your message file. So you might be seeing the messages like numerical singularities, or warning solver problem, numerical singularity when processing node this and this, and then it will be pointing out to the degree of freedom. So the main causes, the physical causes that are happening in the model is unconstrained rigid body motion in a static analysis. So most possibly you have missed a boundary condition. So if you are trying to solve a static problem, you miss a boundary condition, then what Abaqus is trying to do is it's applying the force without seeing the reaction. And it knows that it's a static problem, but there's no reacting force to it, then the body will start moving in a rigid body mode. And that will lead to the convergence. So it will give you this type of warning, and eventually the analyst will exit with an error here. So you can see from the picture on the right hand side, this is the typical type of warning that you will be seeing. Zero pivots. So it's unconstrained rigid body modes and over constrained. So for example, in certain regions where you needed to define the boundary condition, you define the boundary condition, but then you define certain other conflicting boundary condition, or you made it like a slave node or slave surface or the master surface at other point, then that may also lead to the unconstrained region. So Abaqus may not know exactly what is the boundary condition. Then it tends to ignore every constraint on the body. Then you are left with the zero pivots. So zero pivots is like sort of a mathematical term, but what it means is that body is really unsupported. So once you apply the force, the body will start moving in a rigid body mode. And that is not acceptable for a static problem. So it will exit with an error. Negative eigenvalues. So it's a loss of stiffness of solution due to material instability or high loading. So maybe you have your material data is maybe incorrect, or maybe material data might be correct, but you have probably applied like a very large amount of load. Or maybe if that is what your actual intention was, then maybe you are correct, and if you want to assess the stability of the system. But most likely, I mean, this might be a modeling error. So you need to probably take a look at your material data, make sure that your units, force units, and the material data units are all correct. Excessive yielding, so this might be a true error. I mean, it may lead to the convergence problem. This might actually be a true indication. So it is the relatively light deformation due to plasticity. So you'll be typically seeing warning message like the strain increment has exceeded 50 times the strain to cause first yield at 48 points. So what it means is that maybe actually the material is undergoing large plasticity, or it is undergoing large deformation. So the load that you are applying is too large for it to handle. This might be an actual design issue. So we need to be aware of what is the actual design issue, what is the error. So it's due to plasticity, so might be usually related to loading. So if your loading was actually in the correct units and the material data was in the correct units and the loading applied is causing this much, then it is actually the design issue. So maybe you need to reduce the load, you need to increase the material cross-section dimension, or you need to maybe have a better material, or it might be the material data. So maybe the units are inconsistent, or maybe the material is too soft for the loading, and it may also be due to the mesh refinement issue. So sometimes the mesh refinement, if the mesh is not fine enough, then the elements will get distorted very easily under the given applied load, and that will lead to the errors. Then another possible cause of the convergence problems might be due to the element distortion. So right from the beginning, you should make sure that always your part and geometry is clean enough. It's good enough. There are no cracks, no undesired features in your part. Then when you are making the mesh on it, the mesh comes out to be good. I mean, it should be like a regular shapes, types of elements that you are seeing, not, for example, on the right side, as you are seeing on the bottom right picture, you are seeing excessive distortion warning. So your green element is basically totally distorted, possibly due to some meshing error, or due to some partition. So you have to proceed fairly carefully from the part module to the mesh module, make sure that your elements are correct, they are well defined, they are regular shape, there are no initial distortions in the elements, because generally these initial distortions may give rise to the problem. So the way to get around it is to do the partitioning, and you want to do the refined meshing. Also, the element distortion may happen due to the incorrect material properties, loads, and/or element shifts. So these are the typical causes. So these slides basically lead you to basically where to look at, and also to try to take a look at the STA files and the message files to make sure that what is going on here. So those files basically give you the spot messages. I will come back to that. Then another problem might be the hourglassing. So it's a mesh instability which affects the first order reduced integration continuum and shell elements. And what happens is that, for example, on the right side on the picture, as you are seeing that we are applying bending moment to a beam, we would like the beam to basically be deforming on the expected deformation, which is the nice shape on the left side, on the second row. But due to incorrect adjoint formulation, it will actually be just showing some shear behavior, but not really the bending behavior, which is clearly physically incorrect. So they are unable to curve because of the formulation restriction. So then this means that you need to change the formulation of the element. Then rather than going with the linear element, you should go with a quadratic element, or a higher, or like a quadratic element, or higher number of elements through the thickness. So here on the bottom, as you are seeing, when I'm subjecting the plate to a vertically applied load, the elements are distorting like this, and this is physically clearly incorrect. So this hourglassing may also lead to the convergence problems. I mean, it is generally not as widely prevalent type of problem as I have seen in my experience, but it may exist. So all the analysts need to be careful about this problem, that you should have to have generally for the plate or the pipe type of structures, you should try to have at least two or more elements through the thickness of the appropriate formulation, so that you don't run into these types of problems. So now, understanding and diagnosing the convergence problem. So Abaqus provides you several good tools through which you can try to get down to the root of the problem. I mean, it is not a very easy job, but at the same time, Abaqus does provide you some good tools through which you can actually look at the problem, see where the problem or the convergence is happening. So first of all, when you are running a job in your job directory, either I will be showing you that one, or through the CAE right now, if you click the right hand side and then the monitor, or maybe you go through the manager and then click the monitor, then it brings out the job monitor as to how the job is progressing. And here you'll be seeing several tabs, such as log, errors, warnings, output, data file, message file, status file. These are very important files here. So if you take a look at the data file, which is abbreviated as .dat, or the message file, which is abbreviated as .msg files, they can give you some very valuable information about whether the solution is converging, what is the type of problems. I mean, it may point out to certain instances in your model in which the problem is occurring. Sometimes the messages may not be very direct. So, I mean, it requires some experience and some searching on your part to basically try to diagnose, but it will give you some type of hint in a certain standardized way, which is built in Abaqus to lead you to this type of problems through which you can diagnose it and try to correct it. Another important tool in Abaqus is the tools if you go to the visualization module, then under the tools, job diagnostics. Then once you open the job diagnostics, here it basically tells you that in which step you are having the problem of the increment, and then these red exclamation marks are the ones where it will tend to point out to you what is happening with the displacement, rotation, residuals, or the contact problem. So you can see several tabs in here. So make it a habit to basically use this job diagnostics and the message and the MSG and the STA files. That should benefit most of the users, and that has enabled most of the users to actually diagnose their apparently very difficult problems to make their solutions converge and have a reasonable solution. So here, once you highlight this, you will be seeing this highlight selection in viewport. Then you can, in the ODB, you can actually see the regions which are giving the problems. And then you can take a look, go back to your model, and then see what you can do over there, or whether there's some sort of over constraint, or whether the mesh is not good over there in those regions, or what you can do over there to basically correct the mesh, maybe do the refinement, or maybe if the mesh is right, maybe there are certain over constraints, maybe it is not supported, it should have a static support over there or something like that. Here, I mean, it's like a typical job directory. Basically, I mean, wherever you'll be submitting your job. So as I was talking about those DAT and MSG files, so several types of files are generated. I'm including your input file, which is like your basic file to which the job is submitted, to the DAT and the MSG files. So these are the very important files to look for. And whenever you get into the convergence problem, at least you should take a look at them. So .dat file basically can point out to you that whether there are error messages or any other problem, then it may possibly point out to you towards an MSG file. And here in the MSG file, .msg file, you open it, and these files are basically openable by a standard text editor. So once you open it, then here you need to take a look at the average force. So average force is something. So remember that we talked about that green curve, that load versus displacement. So the average force is something which is computed within Abaqus from the model, which is the resultant, you can say, on the elements of the applied force at that section. And then the largest residual force is the residual, that I1 that we were talking about. So that is the difference. That's sort of the error between what the actual solution should be and between what Abaqus is doing it at that moment. So I mean, if the largest residual force keeps on increasing, then this means that the problem is not converging. So as you can see here in the MSG file, force equilibrium not achieved within tolerance. So this means that it will either take some more iterations. So you need to keep an eye on those iterations and see if your largest residual force is decreasing with the successive increments. If it is not, then probably the solution may not converge easily, or it may have some issues. So these are my general tips for modeling solving the convergence problem. So as analysts, we tend to throw everything into the model right from the very beginning, and we tend to solve the problem immediately. But the expert advice is this, that I mean, if you are really working on a complex model which involves so much complexity, so many different bodies, like some 10, 15 different components which are going to be interacting, and if it involves a large deformation, possibly a large deformation, and the material nonlinearities, then just build up your model gradually, one by one. I mean, just keep including the complexities in a stepwise way. Don't put everything all at once, because generally, I mean, the model may have some convergence issues. Test the model for simple scenarios, such as just apply the gravity or some other simple load or boundary condition to assess whether the model is working. For example, if you are working in a static model, just apply the model. I mean, if you are working if you have the gravity present, without checking any other loads, first of all, just apply, test the gravity with a very simple material model, see if the model is working, if the contact is established, so on and so forth. Gradually adding the complexities and seeing the convergence problems points out to the factors that are contributing. So here you can, through a process of elimination, a logical process of elimination, you can find out what is causing the convergence problems. Ensure, now this goes back to the basic, ensure that the part geometry, mesh, and elements are all very well defined, very proper, without any distortions in their shape. Always ensure that the forces, goes back to the classic point, that the units of forces, material properties, and displacements are consistent. So as you know, you are well aware that in Abaqus there are no units. So you should always make sure that everything, the system of forces, pressures, then the material data, everything, and the displacements are in consistent sets of units. Use available tools, job monitor and job diagnostics. So job monitor for checking the ST and MSG files, and job diagnostics to point out to the physical regions in the model, to see the error messages, warnings, and the convergence behavior of your model. So basically this concludes my presentation here. I mean, as I mentioned to you, that it's a very broad topic. It's not possible to do complete justice to this topic in these near 40, 50 minutes or 1 hour. But if any one of you is interested, then of course you are more than welcome to register on our website for modeling, contact, and resolving convergence issues in Abaqus. We offer this 3-day class, which involves several hands-on workshops and in-depth detailed theory to basically understand the contact and convergence problem. So this concludes my presentation. Please let me know if you have any questions.